So we've talked about a frequency table. We've talked about a histogram. Now we need to talk about another kind of table, a relative frequency distribution. The relative frequency distribution includes the same class limits as a frequency distribution, but the frequency of a class is replaced with the relative frequency of the class as a proportion or as a percent. Maybe instead of wanting to know just how many people had pulse rates between 60 and 69 and how many have pulse rates between 70 and 79, maybe instead of how many, we want to know what percent. What percent of people had pulse rates between 60 and 69? What percent had pulse rates between 70 and 79? How would, if we knew that 12 people fell in this class, how could we find what percent of the total that is? By the number of people, let's see, I don't know if we were told how many people that was, 37, 40. That's 40 people. So 12 divided by 40 would give us the percent in this class. 14 divided by 40 would give us the percent in this class. Yes. Yes. Or you could have counted how many numbers were given to you on the initial data table. But since you already have the frequency distribution, just add up all the frequencies. So here was our frequency table for the pulse rates. Here's our relative frequency table for the pulse rates. It's just these values, each of those values divided by 40 gives you the percent of individuals that fall in each class. So we can do the same thing with our cigarettes. I recopied the frequency histogram here because I didn't want to have to flip my page back over to look at it. These are the same classes we had from the previous page. These are the frequencies we had from the previous page. How many cigarettes were in this study? 25. You can either count how many were on the original table or just add up those frequencies and you get 25. So what percent of the cigarettes fell in the range of 0.2 to 0.3 milligrams of nicotine? 1 out of 25 is 4%. Just punch on the calculator, 1 divided by 25, and then change it to a percent by multiplying by 100 or moving the decimal 2 places to the right. So first class had 4%. Second class had the same frequency, so it would have the same percent. Third class is also 4%. The next class had a frequency of 8. And I know a lot of you have already grabbed your calculator, but if a frequency of 1 is 4%, then what's a frequency of 8 going to be? 8 times 4%, 32%. A frequency of 12 would be 48%, and a frequency of 2 would be 8%. How could you make sure you didn't just make a math error punching on the calculator? What should those percents add up to? 100%. Let's see if they do. There's 12 and 32 is 46 and 48 is 94 and 92. 92 and 8 is 100. Let me double check that. 12, 44, 92, 100. 100%. So without that middle column, which I only copied so I didn't have to flip over and look at the other side of the paper, without that middle column, that is a frequency table, or a relative frequency table. And we could make a relative frequency histogram. I don't think we will. You know, just to save time, it's going to look just like the other histogram, but rather than having the frequencies up the vertical axis, it will have the relative frequency or the percents. So the top bar would need to go up to the highest percent is 48%. If your vertical axis was just labeled, say, 0 to 50%, that would be good enough. All right, let's talk about one other kind of frequency distribution. We've talked about a plain old frequency distribution, a relative frequency distribution, and now we want to talk about a cumulative frequency distribution. Remember when I said you can just look at the frequencies for each class in the cigarettes and tell that a vast majority of the cigarettes had 0.8 or more milligrams of nicotine? I was really giving you a preview of the cumulative frequency distribution then, rather than just telling me how many people had pulse rates between 60 and 69, how many people had pulse rates between 70 and 79. I want to know what percent of people have pulse rates less than 70. Not percent. How many people have pulse rates less than 70? How many people have pulse rates less than 80, less than 90, all the way up to everybody had a pulse rate less than 130? So just start with less than the lower limit of your second class. Everybody that fell in that first class was below 70. So the first class in your cumulative frequency distribution would be less than 70 is this 12 people. Less than 80 would be this 12 people plus this 14 people. Less than 90, just add up all three classes until you get to the very last class, less than 130. Everybody was less than 130. So the cumulative frequency on that last row should include everybody. Here are all three frequency tables for the pulse rate. The very simplest frequency distribution, the relative frequency distribution, just converts all of these to percents of total, and then the cumulative frequency distribution, which doesn't have the upper and lower class limits, but it's just less than 70, less than 80, less than 90, and so on. So let's do the same thing with our cigarettes. Use the same data to construct a cumulative frequency distribution. Well, right above that, we have our frequency distribution. No brand of cigarette had less than 0.2 milligrams of nicotine. Only one cigarette had less than 0.4. So that's going to be our first class. Our first class will be less than the second class, or less than 0.4 milligrams of nicotine. And then just use your other lower class limits. We'll have less than 0.6, 0.8, 1.0, 1.2. Now, if we stop at less than 1.2, we're going to miss some brand of cigarettes that had 1.3. We have to go one class beyond that to less than 1.4 so that all of our data values falls into one of those classes. How many cigarettes had less than 0.4 milligrams of nicotine? Only this one in the first class. That was the only brand that had less than 0.4 milligrams of nicotine. How many had less than 0.6 milligrams of nicotine? Well, here's 0.6. There are two lower than that. How many brands had less than 0.8? Well, this one, and this one give us 3. How many less than 1.0? These 3 plus these 8 gives you 11. How many less than 1.2? These 11 that we've already counted plus these 12, 23. And how many less than 1.4? All of them. In a cumulative frequency distribution, you're adding the frequency for the cumulative frequency for the previous class to how many fell into the next class. Everybody falls into the last class. If not, then you don't have your last class labeled correctly. No. All right. So what can we tell by looking at these frequency tables and these histograms? Cigarettes are bad and your heart beating is good. That's what you can figure out. Later we'll make a big deal of a normal distribution. This section just mentions it briefly, gets it in your head, and says we'll come back to it later. But a normal distribution is also called a bell-shaped distribution. And I bet a mental image pops in all of your heads when I say the bell-shaped curve. It starts low, reaches some peak, and then goes back to low, relatively symmetric. The frequencies start low, increase to 1 or 2 high frequencies, decrease to a low frequency. When data fits that shape, you say the data is from the normal distribution. And when you're looking at the graph, you say that's a bell-shaped curve. The distribution is approximately symmetric with frequencies preceding the maximum up to the peak, looking pretty much like what comes after the peak. You could fold it in half and the two sides would match up pretty closely. Was that the case for the, there's a picture of the histogram. Was that the case for the histogram of pulse rates? No, that's not even close to a bell-shaped curve. Those pulse rates are not normally distributed between 60 and 129 beats per minute. It's not true for the amount of nicotine either. If you look at that graph on your paper, that is not bell-shaped. It's not symmetric. It's skewed much more toward one end than the other. There were very few low amounts of nicotine. Most had the high amounts of nicotine. But if you look at this other picture did I put it on here or just the other page? That. That represents some data that is normally distributed. Starts off with a low frequency, reaches one or two high frequencies, and then tapers back off, roughly a mirror image of the left-hand side. So you could look at that histogram and say, that's from a normal distribution. If you look at the graph, you say, that's a bell-shaped curve. Now, I think there's one other graph that I put on the handout. Well, not graph, but a frequency distribution. And I put a couple notes here about the normal distribution, the ones I've already mentioned. This table 2.5 in example 2 gives a frequency distribution for IQ scores. IQ scores are normally distributed. An average IQ, do you know what number on the Wechsler scale corresponds to an average or mean IQ? 100. 100 is average. Below 100 is below average. Above 100 is above average. They're normally distributed. It makes sense to say most people are average. That's kind of the definition of average, although it's not true to say you have the average number of feet. Remember that? Average number of feet. You have the median number of feet, but not the mean number of feet. Average IQ score is 100, so the vast majority of the population their IQ falls between 90 and 109. This is out of, I think, 1,000 people. Out of 1,000 adults, almost half of them fall in that one class. And then a class below and a class above also have close to the same number of people. 2 classes below and 2 classes above have very close to the same number of people. These are your Mensa folks right here, your geniuses. So you can look at a frequency distribution or a histogram and determine whether or not it's from a